All right, so let's move on to convolutions. So our convolution neural networks, we'll talk about this today and then into tomorrow, but kind of like a little bit of transfer learning and stuff like that too. So convolutional neural networks, you can find the, what's it called, the notebooks within like this part deep learning convolutional neural networks, is basically mostly used for image, like image recognition, stuff like this. The idea here is that we're going to use, well, the classic example is using image recognition, but it's actually useful for a lot of other things as well. So the first thing to do, where is this an old version? Okay, we'll skip over that for now. Sorry, usually I have a table of contents, which means this is probably an older version, but we'll see what happens. So one thing to kind of look at is like, okay, the classic example is just computer vision. And it turns out neural networks do a pretty decent job, but there's some issues with it. So I'll kind of show you a little bit of like, if we attack this with a neural network, what this would look like. So one thing to note is that images are just values. So when we see an actual image, I don't know if anyone's familiar with this, with like digital photography and whatnot, but the idea is that if we have an image like this, I'm gonna draw my person. Okay, is that we can split up, and this is going to be really simplified, is that we can split this up into a grid, essentially. And this is going to be a really low resolution picture, but the idea here is that we split up into a grid. And each of these values in here, each of these pixels have some value between like 0, we'll say between 0 and 1, but usually like 0 and 255, basically like the different color, like intensity. But you can basically say there's some value in there, some numeric. And basically if there's nothing in there, it's 0. If it should be brighter, we turn it up to like 1. And this would be basically saying that we can take up all images and break them down into the pixel values. So note that grayscaled images are essentially just a 2D picture. So if you see a 2D picture, it's just a grayscale 2D picture. It's essentially just values of like, let's say between 0 and 1. So each box has 0 to 1. However, if we have colored images, note that basically there's going to be, like if you heard like RGB, right? So like RGB values, is that essentially we have 3 different layers on top of one picture. So it says how much red is there, how much green is there, how much blue is there. And so you usually see this represented, for example, I'm not the best drawer, but let me just do this quickly, is that if you imagine this is the red layer, and then in that picture is the blue layer, and then you can imagine there's like a person that's the picture, but in the blue side, and there's like a green layer. So when we can think of this as kind of essentially as a 3D tensor. So this all together here creates one picture that's in color. Okay. Cool. So just kind of know that difference here. In general, we're going to look at, right now, we're going to look at grayscale, but know that you can extend this out into multiple colors. So this is why neural networks aren't really great at doing image recognition, okay? One is that we have to feed in a vector. Here's the problem, is that if we have a picture like this, and we split it up into a grid, okay, the way we can kind of imagine this, let's imagine this is like A, B, C, and the next one is like D, E, F. We'd want to put this into a vector. So this might look like then if instead of a matrix would look something like this, where we have A, B, C, D, E, F. The problem is that we're losing some information here. We're actually losing like this spatial information. So for example, you can see right here is that A, B, and D, and E are actually pretty close together, right? The problem is here is that we have A and B close together, D and E close together, but they're kind of separated out now. They're no longer keeping that information they're close. So if you imagine this is like your eye here, and this is maybe like, I don't know, like a little bit lower, like your nose or something like that, your eye is going to be right here, but your nose is going to be all the way over here. So this is actually going to lose some information about how far away things are from each other. So the problem is that neural networks, you know, the way we've learned them so far, they have to be flattened. They have to be basically taken from a tensor, a 2D tensor, a matrix, into a vector, otherwise we can't do it. So we can actually lose some multidimensional patterns and structure and stuff like this. So this is where convolutions will do really well. But for very simple images, you actually find that neural networks do a pretty decent job. So just kind of showing you a little bit like what this looks like, and then we're going to extend this off to convolutional neural nets, is that we can first say, okay, let's go ahead and load in some data. So in this case, Keras has some data set called fashion MNIST. MNIST, do you guys know what that data set is by chance? Okay, so I see some nods. So like it's basically hand-drawn numbers of 1, 2, 3. Fashion MIST is basically kind of the same idea where it's black and white grayscale images, but they're pictures of kind of like clothing items and stuff like this. So this is actually, I think, is a little more interesting than just numbers by itself. So you can see here for something that looks like a shirt, I think it's like a tank top. There's different classes of, oh, this is like a shirt as well. And this is like a shoe. There's different classes. I'm going to pull this up. But the idea here is that we can pull up different, like we can actually do image recognition, but it's just grayscale. And note that you can see it's really pixelated, right? Because essentially it's relatively small. I think it's 20 by 28, if I remember that right. Maybe not, no. But anyway, you can kind of see like, here's the little grids right here. And so we can actually do a pretty decent job on this. Now note that I mentioned 255 here. What we have to do, essentially, this is in between 0 and 1. And our neural networks work really well when the values are between 0 and 1. So what we'll do is actually scale it down to by 255. So if I just quickly show you X-train here. Oops. You can see here, oh, this is a great example. Let's see here if I can get something real quick. There we go. So you can see the values here are basically going from 255 to 223 and all this stuff. The problem is like our neural network's just not going to do a great job doing this. So what we can do is we can scale it down by dividing by 255, since that's the max value, and this will make it down from 0 to 1. So if I run this now, this scale it down 255, and you'll notice now if I run this again, which remember 14, 54, 255, 223, you'll see they're all be decimals now. Okay, so now it's all set for our neural network to actually feed and kind of go through. Okay. So also note that I'm just going to do a quick one-hot encoding for the actual category. So instead of having like 0, 1, 9, whatever, I'm going to one-hot encode it. So it should be, it's either a shoe or a shirt or not, or something else. Okay. So our basic model, I don't need to kind of go through this part right too much. We see like we're building a sequential model. So we've seen something before. Note that I have to add this flattened part right here because essentially I'm taking that training data, which is a matrix, and I have to flatten it down into a single vector so I can feed it in. Those are all inputs. So if I run this now and you see the model summary, you can see our first part is 58,875. Want to square root of that by chance? No. Let's see, NP. Okay, about 240. So it's about 240 by 240. Let's just round it up a little bit to 43. So anyway, this is the number parameter. So you can see already we're just feeding this in here to different layers, and then we'll have a total of 65,000 something weights to mess around with. Okay, so we can go ahead and compile that. You can see I'm using the optimizer natom here, the metrics. And I can go ahead and train it, which means basically I'm going to go ahead and process that thing through feedback and stuff, or through back propagation and everything like that. I'll do it for 8 epochs since we have a limited amount of time. Go ahead and run this guy. And we can see now, you can see it go a lot slower now. You can actually see this estimate time, and you see the loss and the accuracy. And then when this is done, you'll see the validation loss, validation accuracy. So this is probably a good idea just to see like what this looks like. So these are just evaluating. So you can see hopefully is that the validation accuracy should improve as we go through multiple epochs here. And I don't know if you can hear my computer kind of start whining a little bit because I have a strong GPU. But so, hey, like you're doing a lot going on right now. So note that if you're trying to do, especially image recognition, you're probably going to want to use a GPU, which can be like Google Colab and whatnot. Okay, and you can see here it's improving a little bit, and you can see maybe start overfitting a little bit, right? Maybe just kind of bouncing around a little bit. And so our final part, it looks like our validation accuracy overall is 0.88, so about 88% validation accuracy, right? Note that I also have this saved to our model.best, so I can save it for later and try it out. Just a quick evaluation, you can see what this looks like. And on this test data, we have about 87% accurate. So not too bad, right? Now, this is not too bad of a thing when you have something relatively simple and relatively like low resolution. But if you have something a little more complicated, like, trying to compare something like a cat versus a person, neural networks in general just tend to be complete trash. Like they just don't do very well just because they're losing a lot of spatial information. And this is where convolutional neural networks will be really useful in kind of getting out this spatial information in addition to just like on and off switches.